Hello, students. Let's start by thinking about the world around us. Have you ever wondered what makes water, ammonia, or even the oxygen you breathe stable? It's all because of valency, the ability of atoms to combine with others. Imagine two people holding hands. The number of fingers each person can extend to form a bond with the other is like valency. In simple terms, valency tells us how many hydrogen atoms an element can combine with or displace in a compound. So, the next time you look at a molecule like water, remember that it's the result of hydrogen atoms combining with oxygen, driven by their valency. For example, oxygen has a valency of 2, meaning it can bond with two hydrogen atoms, forming water. Equation: hydrogen gas plus oxygen gas gives hydrogen chloride, written as H2 gas plus O2 gas forms 2HCl gas. Now, let's dive into something interesting: variable valency. Have you ever thought why some metals behave differently in various reactions? Well, that's because some metals can exhibit more than one valency depending on the conditions. Take copper, for example. It can show a valency of +1 in copper chloride or +2 in copper sulfate. This flexibility comes from its ability to lose electrons from different electron shells. Think of it as a person who can use multiple hands to form different types of bonds. That's variable valency in action. Example: copper plus chlorine gas gives copper chloride, written as Cu plus Cl2 gives CuCl, and copper plus oxygen gas gives copper oxide, written as Cu plus O2 gives CuO. This ability to switch valencies allows these elements to form various compounds, making them incredibly versatile in chemistry and industry. Let's shift gears and talk about radicals. You may have heard the term radical in other contexts, but here in chemistry, a radical is a group of atoms that behaves as a single unit and has a particular valency. Think of radicals like team players in a chemistry game. They stick together, maintaining their own charge or valency. For example, the ammonium radical NH4 plus carries a charge of +1, and it can combine with other ions to form compounds like ammonium chloride. Example: ammonium radical plus chloride ion gives ammonium chloride, written as NH4 plus Cl minus gives NH4Cl. Here, ammonium and chloride combine to form a stable ionic compound thanks to the valency of their radicals. Radicals are essential in forming many compounds, and understanding them helps us see how elements come together to create new substances. Now, let's talk about the metals, which have some interesting stories behind their symbols. Did you know that many metal symbols are derived from their Latin names? For example, copper is represented by Cu from the Latin word cuprum. Similarly, iron is Fe from ferrum, gold is Au from aurum, and mercury is Hg from hydrargyrum. This tradition of using Latin continues to this day, and these symbols are recognized all over the world. So, when you see Ag for silver or Pb for lead, you're looking at symbols that have been around for centuries, linking modern chemistry with its rich history. Radicals also play a crucial role in chemical reactions. They're not just passive participants, they actively combine and form new bonds during reactions. For example, when ammonium NH4 plus reacts with chloride Cl minus, it forms ammonium chloride NH4Cl. Radicals combine to form stable ionic bonds, and this happens all the time in both organic and inorganic reactions. Example: NH4 plus Cl minus gives NH4Cl. Notice how these radicals combine to form a new compound thanks to their valency and charge. In nature, such reactions are essential for processes like nitrogen fixation in the soil, where radicals play a key role in forming compounds that plants need to grow. So, to sum up, we've learned that valency helps us understand how atoms combine, whether they're losing or gaining electrons. We also explored variable valency, where some metals can exhibit different valencies in different compounds. And let's not forget radicals, groups of atoms that stick together, showing a consistent valency and playing a crucial role in forming new substances. These concepts are more than just theory. They're behind everyday reactions, from the rusting of iron to the formation of the air we breathe. So, next time you see water, ammonia, or even a salt, you'll understand how valency, radicals, and chemical formulas work together to make life happen on a molecular level. I hope this session helped you see how chemistry is more than equations, it's the invisible force behind cooking, cleaning, fueling, and even healing. Catch you in the next video. We will discuss the valency chart, where we'll explore the valencies of common elements and how to use them in chemical equations.